Okay, so next let's talk about how to train the Gcm model as we discussed before. Before we have mentioned how to define the architecture for the Gcm model already, right? By stacking multiple SGC operator on top of each other, then we can define the architecture for the Gcm model. Also, we can further calculate the representation we can learn from layers, from the final layer of the Gcm model. Then in the next part, we can discuss how to train the Gcm model, with some tasks. Right now, we have different versions of the Gcm model proposed already, and we can also discuss their training in this part. And for the existing graph neural networks, many of them depends on the Gcm model we just discussed before. So for the vanilla Gcm, we can build the Gcm by stacking multiple SGC operators on top of each other to build the model architecture. And besides the vanilla Gcm model, we can also have different variants of the Gcm model as well proposed, like the GAT model, ADA GCM, GResNet, APPMP, and so forth. In the following part, we also discuss the GAT model as well for you. What will be the difference between the GAT and GCM as we discuss here. Besides the models based on the Gcm model, we also have some new architectures proposed in recent years, which is based on transformers and BERT we mentioned before, right? And we have graph BERT, SEG BERT, and G5, and so forth. We will also discuss the GResNet together with the graph BERT in the following lectures as well for you. So as to the training process, for training the GEM, we have different tasks that can be started, right? Some are based on supervised learning, some are based on unsupervised learning. So for the supervised learning, normally we will require to introduce some supervision information for learning the model, right? Then we can define loss function and to compare the prediction results with the ground truth. So we can start different kinds of problems, for the supervised learning based training of the models, like for the node classifications. Because in some graph data, we have some labels assigned for the nodes. Now in a movie data set, we have movie, we have actors. For different movies, we also have different genre or some other attribute information, right? In other words, for the nodes, for the movie nodes inside the graph, they will be assigned with some labels. It will be similar for the online social networks when we have a user, right? And we can distinguish this user from other users by assigning them with labels. Based on the jobs, or based on the gender information, or based on some other information. We can easily classify the nodes in the graph into different categories or different classes. So we know we have learned representation for the nodes already according to the previous discussions. Then we can further utilize these learned representations and to classify the nodes in the graph. To project the nodes to their labels and further minimize the classification loss. So besides the one which requires the supervision information, we also have some other tasks which don't require any supervision and information at all, which are for the unsupervised learning of the graph neural nets. For example, we know that for each node we have the input features, right? For the nodes. And we may also want to ensure probably, the neural embedding vectors for the nodes can recover the raw features of the nodes, right? Then we can define a task for the node raw feature recovery. In other words, based on learning embedding vector, we can further recover or reconstruct the corresponding raw features in a very similar way like the autoencoders, right? And we can project this embedding vector to their raw features again and compare with the true raw features, right? We can define loss function for training the model. And some also rely on the graph structure reconstruction, because right now we have mapped all the nodes in the graph into their embedding vectors already. And sometimes you need to ensure these nodes can capture the graph structure information. In other words, based on the embedding vectors, we can further infer the connections among different nodes, right? Based on their embedding vectors. Then we can define some tasks for the graph structure reconstruction task as unsupervised learning task for training the models. So these are the different kinds of problems or tasks we can start for training the GM models. In the following part, we can take this node classification as an example for you to illustrate how can we learn the models. So the node classification will also be started in your project stage 5 as well for this course. So we will classify the labels for each node in the data set, in the graph data set. Then we can train the GM model or the GCM model for you, right, in the project. Okay, then let's see how can we train a GCM model, by utilizing the graph classification task as an example. So here we assume for the nodes inside the graph, we have some labels assigned for them. These labels denoting different classes, right? So based on the GM model, either the GCM we have introduced already in the previous part or the GAT to be introduced later. Then we can obtain the embedding vectors for the nodes like VI as ZI as we mentioned before, right? We have illustrated how can we denote these vectors for different nodes in the graph by the formula we show here, right? With multiple SGC layers as we defined before. Okay, so based on the learning embedding vector for the node, not the ZI for the VI node, and we can further project this ZI vector to the labels, right, with some other layers. Now via the multi-layer perception, we can project and model the embedding vector to its labels, right? So by feeding this ZI as an input vector for the multi-layer perception, we can project it to a label vector, the YI hat, right, for the node. This YI hat denoting the prediction labels for the node in the input graph. So we know this denoting the prediction result, right? We can also know the true labels or the ground truth labels for the node VI as YI as shown here. So by comparing the YI hat versus the YI, we can define a loss function, right? And here if we assume we have a training set covering several nodes already, then by summing the loss terms calculated for all the nodes in the training set together, we can define the overall loss function for model training as shown here, right? The A we use here can denote this cross-entropy loss function we used before, right, in your project. That by summing the loss terms together for all the nodes in the training set, we can define the final loss function for the model. So by minimizing loss function, we can optimize the model, so we can learn the parameters inside the model architecture. The W we defined before, right, for different layers. So by learning the model architecture together with the variables inside the model architecture, we can know the models as well. We can compute the embedding vector for all the nodes inside this graph neural networks, right? This is the way we can train the graph neural networks models and also learn the embedding vector for all the nodes inside the graph. So in this task, we assume we know the labels for each node inside the graph. Then we can define loss function based on the prediction result for the nodes and compare with the ground truth. And besides the node classification, sometimes we also have some graph data. We have the labels for the whole graph instead. In the following part, we will show you with some applications. We can have labels assigned for the whole graph. It's not for the nodes. Here we assume we have the labels for the whole graph instead. Each graph will be assigned with a label. So based on Gcm model we defined before, we mentioned we can learn the embedding vector for all the nodes inside an input graph, right? And a VI, that's ZI vector for the VI node. And here, if we are starting the graphs with the labels assigned for the whole graph, then we can further aggregate all the nodes representation together to learn the embedding vector for the whole graph instead, right? So for example, by integrating all the embedding vector for all the nodes inside the graph together, we can define the embedding vector for the graph, like for GI instead as shown here. So we also use this bracket to denote an operator we can use for aggregating all the information together, right? And we can have different way to define the operator, for the brackets. For example, we can define this bracket as the average of all the input vectors as we show here. We have Z1, Z2, and so forth for covering all the nodes inside the graph, right? And we can calculate the average of all the nodes representations together. And we further fit this one to a multi-layer perception to define the overall embedding vector for the whole graph instead, as shown here. So based on this whole graph representation Z as shown here, we can further infer the labels by some models, right? Like Y hat denoting the inference prediction labels for the whole graph instance. And by comparing it with the ground truth, we can further define loss function. So this is task we can start based on graphs. We can do the graph classification instead. Each graph will be an instance, and we can also assign with some labels. And by comparing the prediction result of the whole graph labels with the ground truth, we can define loss function for optimizing the models together with the variables. And we will illustrate some examples for the graph classification in the following pages and how to use this kind of task for learning the models for GM.